In section 3.12, we talk a little tiny bit about organic chemistry. Specifically, we're going to look at naming organic chemistry molecules. Now, just keep in mind this is one tiny section in this part of the book, but in reality, the field of organic chemistry and the molecules and the reactions of those molecules can take up an entire 2 semesters course sequence and still only be touching just a little bit on that subject matter. So we're going to be talking about a very small amount. You're only going to be responsible for a very small amount proportionally of this content. Now, the compounds for organic chemistry focus mainly on compounds that are composed of carbon, hydrogen, and oxygen, and a large portion of them have only carbon and hydrogen. Sometimes we also throw in some extra stuff in there like sulfur, nitrogen, or phosphorus, but that's a little bit more rare. Carbon, hydrogen, and oxygen are kind of the mainstays. There's a couple of new prefixes that we talk about to designate how many carbons are present in a particular compound. These can get fairly large, even though they only have a couple of elements. They form these long chains of molecules of carbon to carbon to carbon to carbon. So we name how many carbons we have present using prefixes. Now, penta through deca we've seen before in the molecular naming system, but meth, eth, prop, and bute for 1, 2, 3, and 4 show a slightly different naming system present for the first 4 numbers. So for the simple alkanes, these are a class of compounds that have only carbon and hydrogen. The carbon is going to form some single bonded backbone, so we can show carbon attached to carbon, attached to carbon, attached to carbon. So this is this chain of carbons that forms a simple alkane. All the non-carbon to carbon bonds are actually taken up by a lot of hydrogens. So we can have all sorts of hydrogens attached to these carbons in all sorts of different directions. And that makes this compound that is referred to as an alkane. Now, hydrogen basically acts like a cap since it only has 2 electrons possible in its valence shell, because it's in that first row. Then effectively hydrogen can only form 1 bond by sharing electrons. So because it can only form 1 bond, it can never be a bridge between things. So it always has to kind of go on the outside edges of molecules. So to name these things, we use that prefix from the previous page, the meth, eth, prop, bute, etc., and we add the ending ane. So all we do is count the number of carbons, 1 carbon. So meth for 1, ane, meaning that everything's single bonded. 2 carbons, so eth for 2 carbons, ane to say that everything is single bonded again. And this kind of keeps going with propane and butane and octane, all things that you've heard about before. Specifically, though, for an alkane, an ane alkane, we're going to have a formula that follows a pattern. However many carbons we have, that's just the number of carbons for N, we'll have twice as many hydrogens plus 2. So if I have 3 carbons, then I'll have 2 times 3 plus 2 hydrogens. So 6 plus 2 would be 8. And that's propane. So if you see just carbon and hydrogen, see if it has this formula to it. And if so, it's an alkane, and this is how you name it. For alkenes, alkenes just means that there's a carbon double bond present somewhere in the molecule. And that's going to take up some of the possible bonds. So there's going to be fewer hydrogens attached to those carbons. But otherwise, this acts just like the other molecule does, with carbons all in a chain, hydrogens are on the outside, and we name it using the same basic idea here, starting with the prefix. But now instead of ane, we use ene, to signify that somewhere in here is a double bond. Well, I can't have a double bond from carbon to carbon with just one carbon, so the alkenes don't start until I have a second carbon at least. The simplest of the alkenes is ethene. Eth for two carbons, ene for a double bond. Propene, butene, follow up, same basic way. Now again, we have a pattern here. And the pattern is that however many carbons I have, I'll have exactly twice as many hydrogens. So if I had C8 for octene, then I would just have 2 times 8, or 16 hydrogens attached to it. Okay, so that's how we name these. That's how we can figure out what the formulas are if we need to translate back from the names to the formulas. Well, we talked very briefly about the double bonds, and we also talked about triple bonds. So if we have a molecule that has a carbon-to-carbon triple bond present, then that's an alkyne, Y-N-E ending. So at least one triple bond, and if that's there, I now am running very short on spaces to put hydrogens because a lot of the bonds with the carbon are taken up with these multiple bonds there. So all the sharing that's taking place of electrons to form this part of the molecule is really being taken up by this multiple sharing from carbon to carbon, leaving not very much room for hydrogen. But again, otherwise, we're looking at the same basic naming strategy to name with the prefix first, add YNE to the ending, and that's as hard as it gets. So 2 carbons, triple bonded would be ethyne. 3 carbons, where one of them is triple bonded, would be propyne. 4 butyne, etc. So the general pattern for the molecules for alkynes, YNE ending, would be twice as many hydrogens, but then subtract 2 from that total compared to the number of carbons. So if we had C8 and this was octyne, so 8 carbons, then we would have 2 times 8, or 16 hydrogens minus 2, so 14. So C8H14 would be octyne, YNE. We also have something called functional groups. So once we start adding oxygens or sulfurs or nitrogens or that sort of thing, we're adding something else to the hydrocarbon, this carbon and hydrogen long chain. And the way we refer to that to talk about these functional groups is with this Rx nomenclature. The R will actually take the place of all of the carbon chain. So we could have this big chunk of molecule, and this big chunk of molecule might be attached to some functional group over here. This whole thing, the carbons and the hydrogens portion, is R. The whole thing is just represented by the letter R. And then X is whatever the functional group is. So whatever that is, as complicated as it is, it's all just represented by something attached to R, to an R group. Okay, blank slide, that's weird. There we go. So the functional groups I can have, the simplest is an alcohol, and an alcohol has a hydroxyl type group, this OH group on one of the carbons, and that's what makes it behave like an alcohol does. And alcohols has a certain set of properties. They're flammable, they evaporate easily, that sort of thing. We use the same basic naming system, but we add anol to the end of it, and that gives us the name of that alcohol. So if we have 1 carbon, and the R group would be this CH3, and the functional group would be OH. So we can call this ROH for this alcohol. But the simplest alcohol, CH3OH, or if we draw out all the connections, it looks like this. This would be called methanol. Methanol. If we had two carbons attached to an OH group with all of their associated hydrogens, then this would be two carbons, so ethanol. And all of these groups have these same kind of properties where there's a name and an ending associated with each known aldehydes and all. So there's all of these different names that go with this. But we're not going to get too hung up in how to name all these different possible substances. We just want you at this point to be able to recognize that these different groups are present. Okay? So anol for alcohols, if it's anal, so methanal or ethanal, that's an aldehyde, and it has this C double bonded to an O and single bonded to an H. If it's just something to a carbon, which has a double bonded oxygen to something else, that's a ketone. So it's very similar here, but there has to be a carbon and another carbon on either side. So aldehydes and ketones are different only in the fact that an aldehyde has one side capped off with a hydrogen. And then carboxylic acids are just named as anoic. So methanoic or ethanoic acid. And like all acids, we throw the name acid at the end. Thiols, don't worry about too much. I just want you to know that if it says thiol somewhere in the name, then there's a sulfur in it. And if it's an amine, then it has a nitrogen group. And they actually classify these as primary, secondary, these little degree symbols, and tertiary amines based on how many carbons are attached to the nitrogen. The more carbons, the farther along this scale that you get. And so that brief kind of glance into this is as much as we want you to know at this point about organic molecules.